Under basic conditions, catalytic methoxide in the methyl hydroxide, compound 1 rearranges through the mechanistic sequence shown below to a propylene type isomer 5. Note that methoxide is catalytic in that it is consumed in the first step of the mechanism and regenerated in the final step. Remember from the general chemistry that the catalyst is the one that's shown in the reactant and still shown in the product side to show that it's not consumed in the reaction. So provide curved arrows consistent with each mechanistic step and resonance structure of 2 that's the greatest contributor to the resonance hybrid. So it's asking us to write the mechanism arrow, the curved arrow, and also the resonance structure of here, the compound 2. Okay, so we're going to start from compound 1 to compound 2, and the key to solve this is to see where the difference lies. Well, the bottom ring structure is still retained, and then the carbon oxygen double bond is retained, and I only see that lone pair is on the ring carbon here. That's the only difference. And you also gotta know that there is the implied hydrogen on that carbon in the ring, and to create that negative formal charge, we're gonna have to cleave up that hydrogen. And where do we get that from? Well, the methoxide. It's gonna be a strong base, so I'm gonna also draw our lone pair to show that that's gonna play a big role. And he's gonna grab that, those lone pairs are gonna grab the hydrogen. And then in turn, we're gonna push that electrons in the bond toward the carbon atom. So we have 2 arrows in this proton transfer. Alright, now we're gonna draw the resonance structure of this compound 2 that's gonna enable to form the compound 3. And if you remember from chapter 2, when we learned the resonance structure, how to draw it, you will see this relationship. Okay, we know the carbon that's attached directly to the double bond will be vinylic, but one that's next to it, right next to it, will be the allylic. We have a lone pair on the allylic relationship here. The lone pair is on the allylic. Therefore, this is gonna allow us to create a resonance, and we can have a nucleophilic attack on the closest bond here, and then in turn that's gonna push the pi bond between this alkene, the carbon-carbon double bond, because the carbon is very unstable to have 5 pairs of electrons around, and we can have that for the second row element. So that pi bond is in turn gonna push or attack on that bond to create a double bond, and then that's also gonna cause the carbon oxygen double bond to place the electrons on the oxygen. So that oxygen is gonna temporarily store the negative charge. So how do we draw that? Well, everything is same. The overall structure is still the same, except we have a minus charge, and then the double bond locations are slightly altered here. Okay, so we have minus charge, And then we have a double bond here. And then we have a double bond here as well. Now you might ask, how do we go from this structure, which is a resonance structure of compound 2, to compound 3? So what's the difference between compound 2, I'll call this 2A and then this to be 2B, from 2B to 3? Well, it's again forming that double bond between carbon and oxygen at the bottom. And then all that bond is now back to where the 2A was. Except of course we don't have the lone pair just like we had in 2A. However, the main difference is that we no longer have the ring structure on that side here that connects the oxygen. So in the I'm talking about this ring here, not the very bottom or the top ring here. Actually top is still gonna be altered as well. Yeah, so I need to break that. Well, top ring is actually reserved, I'm sorry. So I need to break this somehow to create the acyclic in one side here. So instead of having 3 ring structure, we need to have only 2. Well, to do that, we're gonna have to do the nucleophilic attack again. From where though? Well, we have minus charge here at the bottom. Now he's gonna push that toward that bond between the carbon and oxygen to create the double bond. And then again, we're gonna push this pi bond to create another pi bond next to it. And then that's gonna attack, that bond is also gonna attack nearby. And then finally, we're gonna break it to create the minus charge that conforms to compound 3. And then from compound 2 to compound 3 to compound 4, the key difference is that we create a ring again for that from the oxygen. So I'm gonna draw the lone pair around. And then you have to ask yourself, where is it gonna attack? And it has to be over that carbon-carbon double bond, because creating that bond will create that dash, which is pretty much a bond, but except this is in perspective. So he's gonna attack on that side to create the another pentagon ring. And then that double bond is gonna push here, and then that is gonna also cause to create minus charge on the oxygen. And then from this structure to compound 5, so compound 4 to compound 5, we're gonna play the same game again by doing the nucleophilic attack. And then he's gonna so this is fine. Actually, we have to push it again. To where though? So seeing the difference, oh, that's why we have the MEOH here. So he's gonna play as the he's gonna play as the nucleophilic attack on hydrogen, and then that oxygen, the bond between them is gonna create the original MEO minus. That way we have that hydrogen. This hydrogen is embedded here. Okay, if I put that green color on that hydrogen, just one of them has to be here. So that's how you answer it. If you really want to know the identification of each step, so this has to be proton transfer from 1 to 2, because we are grabbing the hydrogen, so this MEO minus acts as the base, and then from 2B to 3, this should be nucleophilic attack, because the lone pair is pushing it. Or you can also think this as the leaving group from intramolecular leaving group, because that bond is now broken. And then from 3 to 4, this is clearly a nucleophilic attack. And 4 to 5, this is gonna be a proton transfer. In other words, we are having the acid-base reaction. So there you go.